Okay, so today I will try to complete the picture with the coding and formation of code. And I don't think we can get to the crypto yet, but then in the next lecture we will. But at least we will understanding what's going on, right? So last time we talked about defining what a code is and creating codes, and we can do it via generator matrices or parity check matrices. And then we hinted at how to decode. Basically, we said, well, the code words have to be kind of recognizable, so the further away they are from each other in the Hamming sense, the more recognizable they are, and we can put them in these little balls, and then we can decode kind of that way. So an important idea is that our coset. So what is a coset? Imagine that I take all the vectors in the space, and I shift them, right? So I take my code, and I shift my code by a fixed amount, which corresponds exactly to a vector in the space. So if I consider that my code is a set of certain code words, x, right? For example, such that, I don't know, x is 0 when multiplied with a certain matrix, right? So it's a bunch of vectors. Then a coset, which we can call, for example, A plus the code, is the set of all the vectors of the form A plus x, where x is in the code. Okay? So you see I'm just shifting every code word by adding A to it.
Yeah.
And so it's coset or sometimes translate. Is really like the idea of shifting the code by a fixed code word, right? And so if we do this, then for every vector in the space, that vector is in at least one coset. Okay? Because for sure, B belongs to the coset B plus C, right? Because I can imagine that if I sum the 0 code word, then that's B plus 0, and that's just B itself. So for sure, B always belongs in the coset that is led by it.
Okay.
Yeah, and now the interesting thing is, of course, if I have two vectors in the same coset, so now suppose that I have a vector A and a vector B in a certain coset, then I have the A minus B is a code word. Okay? Because coset is indexed by say y plus c, and so A will be y plus a code word, and B will be like y plus another code word, and then if I do A minus B, the y cancels out, and then I get like the sum of two code words, and that's a code word as well. Okay, so these are pretty important basic rules, and of course, in every code word, in every coset, I have exactly q to the k words, because it's the q to the k words of the code all shifted by A. So now that we have these cosets, and I say every word belongs in a coset, right? But can it belong in more than one coset? And the answer is no. So we have this result that says that if I take two cosets, they are either disjoint or equal. Right, so they're either disjoint or they coincide.
Okay.
Okay, so we cannot have a partial overlap, and the reason is very simple. Suppose that I do have an overlap, like A plus the code and B plus the code. So I have these two cosets, and I take a vector V in this intersection. Well, then V is going to be like A plus X, right? Because it's in the first coset, and X is a code word, but it's also B plus Y, where Y is a code word. And therefore, I can always write that B is A plus X minus Y. But now I know that X minus Y is a code word because the code is linear, right? So I call this X prime. and this is also in the code. And so I have that B is A plus X prime. But look at this, this means that B is in the coset, this one.
Yeah.
And so this means that one coset is contained in the other, in particular is showing, so this shows that B plus code is contained in A plus code. And vice versa, I can arrange this equation as A equal,
Right.
and then I can show that this one is contained in this one.
Mm.
So then they must be equal.
Yeah.
Okay. So if I have an intersection, then the two cosets overlap entirely. Otherwise, they're disjoint. Okay, so that means that effectively, look what happens. I have f q to the n is my space, and this contains q to the n elements, and I can kind of group them or partition into cosets, right? They contain q to the k each. Okay. So if I have, I don't know, 2 to the 6, like was the case for my code,
Mm-hmm.
right? That was length 6, so 64 code words.
Right.
And then the code dimension is 3, so I have 2 to the 3 code words. So 2 to the 6 is 64 words in the space. 8 of them are code words. And then I can partition the space into like the code words, and then the coset shifted by a certain word, that's 8 more, and then 8 more, 8 more, 8 more. In the end, I get 8 times 8. So I get 8 different cosets.
Yeah.
Okay. And so I can partition the space into these cosets. So now, one thing that that we will talk about is, of course, I have these cosets, right? So they're all defined. They can be defined by any vector in them. So if I have a coset that is defined by like 8 plus the code, then there'll be like many other vectors in there. So I could have chosen another 8 to define that coset. So it pays off to identify one leader, how we say it, like a coset leader.
Okay.
To define a coset. This is not dissimilar from what happened with, for example, the modular arithmetic, where we say we take all the integers and we partition them in like class 0, class 1, class 2, right?
That's what I was thinking of
Yes.
when you were talking.
Exactly.
Yeah.
It's exactly like that. And what do we choose to represent the class? Oh, 0.
Yeah.
Like say we're working modulo 7, then we have class 0, class 1, class 2. Well, then in class 2 you also have 9, right? But you wouldn't say that's class 9, you say it's class 2. You choose the smallest one.
Yeah.
And that's kind of what happens here, except that our measurement tool, in this case, is the Hamming weight.
Yep.
So our coset leader is going to be the smallest weight word in there, the one with the fewest number of ones. Remember, the Hamming weight is how many ones or how many non-zeros if you want, because now we're working over FQ in general. So we choose the least weight one, right? So the coset leader is the minimum weight word in the coset. And now, why do we care about the cosets, right? Because we've partitioned the space into a bunch of cosets, and this will be useful for decoding, right? Because now suppose that I receive a word y, y1, yn, that has been received over the channel and contains some errors. And so this we know is x plus e, right? Where x is a code word and e is my error vector.
Mm-hmm.
So this must belong in a certain code word, in a certain coset, because every word goes in a certain coset. And so, for example, let's say that so let's say that therefore the error is y minus x, right? And I know that y belongs in a coset, say a plus x prime,
Mm-hmm.
right? So if I can find in which coset that goes, well then this is the same as a plus x prime minus x. And this is, again, a code word. And therefore, this means that this belongs in the coset a plus c. And so look at this, it means that the error is in the same coset. Now, of course, because I'm looking for the maximum likelihood decoder, the error will be exactly the coset leader.
Right.
because the coset leader is the one with minimum weight.
Yes.
So if I assume there has been an error on the code word, what I really need to do is find in which coset it lies,
Yeah.
and then find the coset leader, and that's going to be my error vector.
Yeah.
Okay? And this is like one very intuitive type of decoding that is called standard array decoding. Because that's exactly what we're going to do. Is we're going to build an array, which is like a word for a matrix, a table. Okay, and this will consist of all the cosets. So we list all the cosets. So in the first row, we put all the code words. Right? And so we start like the first row is exactly C, and we put the coset leader on the left. And what's the minimum weight word is exactly the 0 word. And then each new row will contain one of the cosets. And we will put the coset leader always on the left. Okay, so here is an example. Suppose that I have that code that I defined earlier that was given by 1001, this is systematic form, 1101. Right, so this is a 4-2 code, binary. I expect it to have to do the 2 4 code words. Perfect. So if I build a standard array, then I have the following code words: 0, 0, 0, and then 1, 0, 1, 1, 0, 1, 0, 1, and 1, 1, 1, 0. Right? These are the 4 code words. Because this is in systematic form, you can see that this exactly corresponds to 0, 0, 1, 0, 0, 1, and 1, 1. Okay, so this is the code here. And then in the first row, so that's my coset leader. In the first row, I will put the first coset. For example, what happens if I add this? Then my coset becomes 0, 0, 1, 1, 1, 1, 0, 1, and 0, 1, 1, 0. Right? That's my, that is the coset defined by this. Right? And then you see this guy is the coset leader. So I choose that to be my A. Okay? Of course, I couldn't choose in this one or this one or this one, but I always choose the minimum weight one. Okay? Then I can do 0, 1, 0, 0, and that gets me 1, 1, 1, 1, and 0, 0, 0, 1, and 1, 0, 1, 0. Okay? And then finally I have 0, 0, 1, 0, and it gets me 1, 0, 0, 1, and then 0, 1, 1, 1, and then 1, 1, 0, 0. Okay, so it's how I expect it to be because I have length 4, so 2 to the 4, 16 words in total in the space. 4 of them are my code, and then I have 3 cosets, okay, with 4 words each. Makes sense? So I partition the space very well, and I have always as coset leader the minimum weight word. Now, of course, you can already see that there's a little bit of a problem here because in this coset I have 2 words of minimum weight. And so this is showing already that this code is actually not good enough to correct an error because there's some ambiguity here. I could have chosen this one as coset leader as well. But if we just ignore this part, then you can see that clearly how do you use the standard array when you receive a word Y, right? Suppose that you receive, for example, the word 1111, okay? This is not a code word, some error has occurred on it, so what you're gonna do is you look for it in the table, it's here, and then shift to the left, and I say, okay, that's my error here, okay? So this one is gonna be 0100, that's my error, plus 1011, which is my code word. So my code word is this one on top. Okay. Now, of course, as I said, the problem with this code is that it's a 2x4 code. The minimum distance is not big enough to guarantee a unique decoding. It could have equally been for example, this error vector, right? And then it would have been a problem because I could have had, so if you see that if I receive 1, 1, 1, 1, I would have also said, oh, the error was this one, and then the error was in the last position and the code was 1, 1, 1, 1, 0. Okay?
Mm-hmm.
So again, this is because this is just an example code. But when we do it with like properly defined codes with a certain minimum distance, then there is not this problem. Okay? There should be a unique minimum weight word in each coset. Okay. So now, how do we find the coset? Well, we kind of have to write down the whole array, which is kind of inconvenient, but we can do it a little bit better. So the next step up to improve this process is to actually look, how can we find which coset is in? Because if my received word is error plus code word, when I do h times y, this is going to be h times e plus x. And of course, this is distributive, so h times e plus h times x. Right? But this thing is 0, right? Because because this is a code word. So h times y is equal to h times e, and so this object, when in general, when you have like a vector times parity check matrix, is called the syndrome of the vector. And so what we can say is that the syndrome of the received word is the same as the syndrome of the error vector. It's called the syndrome because, like in medical, it gives you the symptoms of what is happening.
Yeah.
Okay, so what you can say is that the coset corresponds exactly to the one where I just calculate the syndrome. So the first thing I do that I receive the word, I compute the syndrome, and that will be the same as the syndrome of E. So I can find, so if my syndrome is 0, then I know that what I've received is a code word. And if my syndrome is not 0, then I can map it to one of the cosets. And I can define the cosets by their syndrome. Okay, so what I can do is I can label the cosets with the syndrome by just computing this times h, this times h, this times h.
Right.
And rather than looking for that, when I receive the word, I just compute h times y, and then I look just directly in this column, right? And that will tell me exactly what the error vector is.
Yeah.
Okay. Okay. So we'll come back to this idea, but essentially there is a one-to-one correspondence between syndromes and cosets. Okay. Now, of course, again, this kind of requires you to have like a map of all the code words of the code, so we can't exactly do that, right? But the basic idea of like using the syndromes and identifying the coset is still valid. So, and the idea of syndrome is very important anyway. So let's now see how we can use this idea to actually decode in a useful way. Okay, and so this brings us to the first kind of class of really actually useful codes, which are the Hamming codes. Okay, so we already saw, if I don't remember incorrectly, some Hamming codes, or maybe not. No, we didn't do that yet. Okay, great. So, okay, so the idea is this. Suppose that I want to start from the very beginning and correct just one error. For sure. Okay, no possibility of mistake. So what can I do? What we see here, when you think about it, what is the syndrome of y, right? So my vector E, I'm saying my syndrome of y is the same as the syndrome of E. E is an error vector, so E will look like 0, 0, 0. Oh, there's a 1 here, 0, there's another 1 here, okay? There's like mostly zeros and then a few ones. So if I do H, E, this is H times 0, 0, 0. Oh, there's a 1 here. 0, 0. Oh, there's a 1 here. Okay. And when I multiply this, it's vector matrix. So here I have the columns of H. Let's say that I have like H1, H2, Hn. These are my columns, right? And then I multiply with like this vector. Whenever I have a 1, it's going to select this column.
Okay.
Then I have another 1 here, it's going to select this column, right? And then you sum them.
Okay.
So that is basically like H, say I1 plus HI2, HIW. If I have exactly W errors, let's say, and I use WI because W is exactly the weight of E, the Hamming weight. Right? So if I have exactly W errors, I have exactly W ones, and then the syndrome corresponds exactly to the sum of those columns there.
Okay. Yeah.
Yeah, and so that is why it's easy to use the syndrome to decode. It's important because it gives you exactly it's the sum of these columns here. Okay, makes sense. So yeah, so you can really see, and then we will see in the end what the connection is with the problems that we saw before. Okay, so now again, let's go back to Hamming codes. We want to correct exactly one error, and the syndrome corresponds exactly to a sum of certain columns corresponding to the positions where the error appears.
Yep.
Okay, so if my columns are all distinct and easily identifiable, then computing the syndrome, right, will tell me exactly where the error is. And this is the idea. Suppose that I have my parity check matrix, and this is like n minus k by n, we said, right, where k is the code dimension and n is the code length. This quantity we know is also called R, the redundancy of the code. Right? So basically, this matrix here has R rows and n columns. So how many columns can I have in total? Well, I can only have 2 to the R minus 1, right, columns available, because these are exactly all the possible different non-zero binary vectors, yes,
Yeah.
of length R. So for example, if I have R equal 3, then I have exactly 7, which is 2 to the 3 minus 1, different columns if I exclude 0, 0, 0.
Yeah.
Yes, and so I can put these 0, 0, 1, 0, 1, 0, 0, 1, 1, right, 1, 0, 0, 1, 0, 1, 1, 1, 0, and then 1, 1, 1. Right? These, for example, I put them in increasing order. That is in binary, 2, 3, 4, and whatnot. Right? And these are the binary representations of numbers from 1 to 7. Okay, and so in a Hamming code, we use all of these columns. And so we get a code of length exactly 2 to the R minus 1, or 2 to the n minus k minus 1. Okay, so my length is going to be exactly the maximum possible one. And in the parity check matrix, I have exactly all the non-zero binary vectors of that length. So in terms of code, this is an nk code with minimum distance d, where the n is given by this. The dimension k is going to be the length minus r, because if r is n minus k, then k is n minus r. So this is going to be 2 to the r minus 1 minus r. And then what we can prove is that the minimum distance is exactly 3. Because if it's exactly 3, then 3 minus 1 divided by 2 is exactly 1, and we connect exactly 1 error. Okay? So this, for example, defines a 743 code, Hamming code. Right? Makes sense. It's length 7. You can see it's length 7. The parity check has 3 rows, so the generator has 4. Yes, and the distance is actually 3. So we can take this in natural order of, say, increasing, but it doesn't have to be in this order. We can take them in a different order, and then again we just have a different code. They just have the same code towards, but just like permuted around.
Okay.
Okay, and this brings us to so for example, if I move this is not standard form, right? But I can move this into standard form if I take, for example, 0, 1, 1, 1, 0, 1, and then 1, 1, 0, and then 1, 1, 1, and then the identity matrix, right?
Mm-hmm.
So these are the same columns that I had before, I just moved them around. If this is H, this is H prime, right? They don't define the same code because the positions are moved around. Remember, the condition for defining the same code is that you're changing your basis, so you're multiplying on the left.
Right.
But so if you have H, then like SH gives you a different parity check for the same code.
Mm-hmm.
But this is different. H prime is not in this form, but it is in a different form. H prime, in fact, is H times P, where P is a permutation. Right? Because what this P does, a permutation matrix is a matrix of the form, for example, 1, 0, 0, and then 0, 0, 1, and then 0, 1, 0. This is a 3 by 3 permutation. And what this is doing is it's exchanging the second and third column. You see that?
Mm-hmm.
Right? Because the identity would be 1, 1, 1, and this is swapping the second and third column.
Yep.
So that is what a permutation matrix is. Of course, in this case, P would be a 6 by 6 permutation matrix. And then you see that it has swapped like this column, that's the first one, it swapped it and put it with the sixth one, and so on, right? So this too, now H prime does not define the same code as H, but it defines what is called an equivalent code. And what does it mean at an intuitive level? What does it mean that the code is equivalent? It has the same number of code words with the same minimum distance, and the code words have the exact same weight distribution, right? So if in your code you have one code word of weight 3, two code word of weight 4, and whatnot, then it's the same thing. So it's the same code, but just the columns are permuted. Okay? Make sense?
Mm-hmm.
So for example, here is a code, a 4-2 code. Right? That is a 4-2 code with 4 code words. And here's an equivalent code. And clearly, like these two match, and you can see here that what the permutation did, for example, is exchange the second with the third column, right? So then this becomes that,
Mm-hmm.
and then this becomes that.
Yeah.
So these two codes are equivalent with the permutation 1, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0, 0, 1. That's the permutation there. Let's exchange the second and third column.
Yeah.
Okay.
Okay.
Yeah, so, and everything matches. So in this code, there are exactly 2 words of weight 2 and 1 word of weight 4. And they're mapped to each other, okay, and whatnot. If I had a different code like this, and then, for example, this, and then, for example, like this, right, and then, for example, like this is not equivalent, right, because the weights are different, they're not the same code words. I don't have a word of weight 3 that I can map to this one, like by distributing. Right, so that is not equivalent to. So there's this idea of equivalence of codes, which is important, and in particular, in the case of Hamming codes, it means that we can choose H in this form, or in this form, or in other forms that are more convenient to us. Here's another form. Suppose that I put them in this order here: 1, 0, 0, 1, 1, 0. 1, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1. Okay? So this is again equivalent, I just move the columns around. But then what is particular about this form is that this is circulant. If you look at the first row, And the second row, you can see that the second row is the first row just shifted to the right by one position.
Yeah.
And then we do this again. Right? You just have this like 1, 1, 1 block, and then 0, 1, 0, and then this 0 goes in front. And then same here, the 0 goes in front. So the second row is a shift to the first, the third is a shift to the second. And so this leads to what we call cyclic codes. And so without even proving it, we already gave a hint that Hamming codes are actually cyclic. Okay? Because they admit one matrix in circulant form. We will see cyclic codes later. Okay, so now how do we do the coding? Okay, suppose we're trying to correct exactly one error. It means that I receive a word y, and then what I want to do is compute this syndrome, right? Which should be exactly h times e transposed, right? But e contains exactly a 1 in position I, and then it's 0 everywhere else. So what this HE does is just select one column, okay? And then what I can do is I can just like take that column, and that's the error there.
Yeah.
Okay. So the error is exactly in position I. Okay. So then they are exactly, perfectly correcting single error correcting codes. Okay. So I do have an example here that takes the matrix H, which is this one. Okay, so suppose that, for example, you obtain the code word y equal 0, 1, 1, 1, 1, 0. There's another one missing. Okay, should be length 7. Okay, this is your received word. What you do is you compute h times y transposed. So transpose this, multiply with the matrix, right? That gives you the vector. I should write it as a column because this is a 3 by 6 and this is a 6 by 1, so you get 3 by 1. Okay? So you get this column here. So then you can just go and look for this column in the matrix. 0, 1, 1. It's here. No, actually, sorry, that's the matrix we're using. This one. Yes. That means that my error is in position 1, 2, 3. And so that position 3 becomes 0. Did I have them correctly? Yes. And so then my code was like 0, 1, 0, 1, 1, 1, 0. Okay. Cool. So that is simply, and so that's your code of X. Now look, you didn't have to like write out all the code words or anything, right? But you know now that this corrects exactly because the columns are all unique and distinct, and each one corresponds to exactly one error.
Yeah. Okay. That makes sense.
You have questions about this? So this is like a very simple idea for decoding, but it works, and it is the basis, believe it or not, for like many more sophisticated things. Okay, so Hamming codes are perfectly correct codes with these parameters here, and you can build one for every r. So you can see they are parameterized exactly by r. The length is 2 to the r minus 1. The dimension is 2 to the r minus 1 minus r. And the distance is always 3. Of course, there's a theorem that Hamming proved behind this that shows that the distance is always 3. And these are the parameters for that. So you can have one of length 7 in this way. And then if you take r equal 4, then you get 15. Okay? And so on. So that would get you, for example, a 15, 11 free code. Okay? And again, you can, for example, choose the parity check that has an increasing order, or the one that is like in standard form, or the one that is like in cyclic form, okay, and so on. So now we've got these, and they can correct exactly one error, and we want to see how we can do better than that, but we just want to nail a few more things before we move forward. So one thing that it's important to mention is, of course, you know what the dot product between two vectors are, right? So that is exactly u1 v1 plus u2 v2 plus un vn,
Mm-hmm.
right? And in geometry, for example, or calculus, if this dot product happens to be 0, then we say that the two vectors are
Normal, right?
yes, or orthogonal.
Yeah, orthogonal. Yeah.
Because this really makes sense in geometry, like it's two vectors, like they're actually
Right.
orthogonal, right? And so we can preserve this idea of orthogonality, even though we're like actually working with vectors over finite fields and we're not looking at the geometry of it at all. But we can still say that two vectors are orthogonal if their product is 0,
Mm-hmm.
right? And okay, so then this defines an interesting idea. Suppose that I take a code C, which is formed by a bunch of code words, right? And then I define a set of words U such that U times V is equal to 0 for all V in C. So I take now the set of all the words that are orthogonal to the code.
Mm-hmm.
Well, what happens is that this actually also forms a code, and we call it this way. And this is what we call the dual code of C. So I take all the set of code words, then I take all the words that are orthogonal to that, they form a code themselves. And this is interesting. And why? So when you think about it, what is this code then? It consists of all the parity checks on C. Because remember that the words that satisfy that, okay, great. So then this code, if the original code, G, had the generator matrix G, and H was parity check, right? Then what happens is that G dual has generator H and parity check G.
Yeah.
Aha, that makes sense. And then the code is nicely defined in the sense that if C was an NK code, then C dual is N minus K.
Okay.
Okay. And then the minimum distance is not so obvious how it's related, the one to the dual with the original one. But these two codes are kind of like the two sides of the same coin, right? And the dual is exactly what the dual is the other aspect of it. So you can consider that the code. The code is defined by all the multiples of the generator matrix or all the words that make syndrome 0 with H. Vice versa, you can say, oh, the dual is generated by the rows of H and is the one that makes G equal 0. And of course, the crucial property that ties everything together, all the ingredients, is that H times G transposed is always equal to 0, because G is a bunch of code words, right?
Mm-hmm.
So H times all the rows of G should make 0.
Okay.
Right? So this is kind of like a crucial equation. So that shows that G, is in the dual, of course, because it satisfies exactly all the rows of G. All the rows of G are orthogonal, right?
Mm-hmm.
And therefore, that one is the generator for C and one is the generator for the dual of C. Okay. So it can happen that for certain types of codes, the matrix is, for example, very highly structured, and we have that the code is actually equal to its dual, right? That, for example, implies that G times G transposed is 0. Right? These codes, without any imagination, they're called self-dual.
Yeah.
Right? And again, we can see later what this implies. Okay. Of course, if the code is self-dual, then the dimension K is exactly 1/2 of n, because it has to be K and n minus K have to be the same. Okay. And then we have a relaxation of this, and if the code is just contained in its dual, so all the words of C are orthogonal to each other, but not vice versa, then this is what we call weakly self-dual. And one can show, for example, that the repetition code is always weakly self-dual when n is even. Okay, so that was interesting to put down because we will use that later. And a couple more things before we move on to like more sophisticated code, which is always our goal. Okay, so now a few extra properties. Suppose that I have H to be my parity check matrix of a certain code. This we said is a matrix R by N. Then the code K has dimension exactly equal to M minus R if and only if the rank of H is exactly R. So in other words, if I'm hoping to define a code properly with R rows and N columns in my parity check matrix, then it has to be full rank. Okay, remember that the rank is the number of linearly independent rows. So if, for example, one of the rows is a duplicate or a multiple of the previous one, you know, one could say, oh, this is still technically a parity check matrix, right? But it doesn't define the full code. So full code is defined by a full rank matrix. Okay. And even more important now, the minimum distance D only happens if at least D minus 1 columns are always linearly independent.
Okay.
Okay. Because what it means, remember that the code word makes 0 when you multiply, when you compute the syndrome, and therefore a H times vector is 0 only if this is a code word. But remember that the syndrome is a sum of columns, and if you're saying that the minimum distance is D, it means that to make 0 you need at least D columns to make 0. So that means if you have less than D, they have to be linearly independent. There's no way to get code words with less than D columns.
Yeah.
Okay. So for the code to have minimum distance D, there is the smallest weight, right? And that means that there's the smallest number of columns that you have to sum to get 0.
Yeah.
So when you think about it now, yeah, each code word really corresponds to a combination of columns.
Right.
Okay. And if the code is not binary, it's the same, except that instead of being like just a sum of columns, it's weighted with like, you know, the value of the places of the code word, of course. So it's a proper linear combination with multiples.
Okay. Yeah.
Yeah. You take like 2 times the first column and 4 times the third column and whatever, and then you sum them, and then that gets you 0. Okay, and then that is my code. Okay. And then this leads us to an important bound, which we call the singleton bound. So looking for bounds on codes is one of the things that coding theorists do, to put bounds and to put things into places to understand how things behave. The singleton bound is a very easy one. So if I have C that is an NKD code, then n minus k is always greater or equal to d minus 1. Right? And then we just saw, I mean, the proof is immediate. Basically, n minus k is exactly R, which is the number of rows in the parity check. And we say that's the full rank of H. And therefore, that corresponds to the maximum number of linearly independent columns.
Yeah.
Right? Because if my matrix is R by N, well, the maximum I can hope is to have R different columns, and then it's like a nice little square. But if I add one more column, then for sure this must be one multiple of the previous R ones.
Yeah.
Right? Because it corresponds to like if you try to like row reduce a matrix and that's rectangular, the best you can hope to get is like a big square, and then the other ones will just be redundant.
Yeah.
Yeah. So that is why, and sometimes you can rewrite this bound in this way. The minimum distance is always at most n minus k plus 1. Okay, you just turn it around. And this gives a bound on the minimum distance, you see. So this is already telling you the maximum separation you can have is n minus k plus 1. That's the maximum. So that depends on how you choose the n and the k, of course, right? And so the codes that actually achieve this bound they're called MDS, which stand for maximum distance separable, and are coded such that basically the words are at the maximum distance from each other. Okay. There's other bounds that are interesting and that we may see later, and I may come back to this. Okay. But I do want to move on to a little bit more interesting code, because so far we only know how to correct one error, but then it goes quickly from there, I promise. Okay. So we already talked about fields and how they are basically defined by polynomials, right? Because we take our finite fields and they're like these extensions of the fields. Okay. So now suppose that I want to correct more than one error. Okay. With the Hamming code, I basically have n, which is equal to 2 to the m minus 1, and I needed exactly m parity checks to achieve one error. Okay. So my guess is that if I take now 2m parity checks, then I should be able to correct 2 errors, right? And okay, let's try to construct a parity check matrix in this way. For example, we can take m equal 4 and n equal 15, which was, remember the Hamming code that I told you earlier. If you take m equal 4, then you get the 1511 code.
Right.
And a parity check matrix, I'm not going to write it all, but is this one.
Okay.
Okay, and you can see that these are my columns, 0001, 0010, and so on, like all the binary strings of length 4. Okay. So we can actually, if we write them in this order, these are exactly the numbers from 1 to 15.
Yep.
And we can actually write them as like 1, 2, 3, 4. So I can actually write this one at least. Then my matrix is essentially like 1, 2, 3, all the way to 15 in binary.
Yes.
Okay. And okay. So now we can imagine that each of these is a tuple, for example, like 1 is 0, 0, 0, 1, and so on. Okay. Okay, so now suppose that we said that we have to like add double the number of checks, so we have to add 4 more rows. So my matrix will be this with some other rows, and what am I going to put here? Some number f of 1, some number f of 2, some number f of 15. I just have to figure out what f is so that my decoding actually works.
Yeah.
Okay, so basically each column hi of the parity check matrix will be of the form I, a certain number correlated with I. Okay, what am I going to put? So this is going to be another binary string on length 4. How do I choose it? Yes?
Yeah.
So if I now want to correct 2 errors, that means that my syndrome is going to be hi plus hj, sum of 2 columns, right? Because with Hamming codes was easy. The syndrome was exactly 1 column, boom, I can see it right away.
Yeah.
But now my syndrome is going to be the sum of 2 columns, so it's going to be of the form I plus j, and then f of I plus f of j. Okay? And let's just call this, for practical, like z1, z2.
Okay.
Okay? So how can I choose fi so that the decoder can actually find exactly what I and j are? If I can find what I and j are, then I have the 2 error positions, I'm done. So I want essentially to be able to solve the system I plus j equals z1, z1, and then f of I plus f of j equals z2. Okay? For given z1, z2, I want to solve for I and j. Okay? So all of these are 4 tuples, and like these are 4 tuples of this form. But how can I operate with these? Because I need to like add and subtract and do operations on them. And so what this means is that I have to make these 4 tuples into field elements.
Okay.
That way I can operate with like sums and stuff.
Yeah.
And well, that's exactly the connecting point, right, with finite fields. That's why we use finite fields. Because now this is a vector of binary of length 4. So that means that it lives in f2 to the 4. Right? And remember how this thing is defined f to the 4 is not the same as z16, right? It's not just 1, 2, 3, 4, 5, 15, but it is defined as the set of polynomials modulo is 4, right? Remember, this is like f p to the m, right? Modulo polynomial like x to the m plus other stuff, right?
Yeah.
This is what we saw when we were looking at construction of finite fields.
Mm-hmm.
So it's all going to be basically the remainders of the division with this irreducible polynomial of degree 4. The hint here is that if we take 4, that's going to be x to the 4 plus x plus 1. Right? So you take all the remainders, and those are your classes. Remember, like we did for integers again, and those are, so you're going to have the polynomial 1 x, 1 plus x, x squared, 1 plus x squared, etc., etc. And to each of these, because this is 2 now, so this we're taking only the binary polynomials, right? To each of these we map exactly one binary string, which is the string of the coefficients of the polynomial.
Right.
Okay, great. So we already done all this here in the book. It does it for you, but basically what you're constructing is f16. I really actually like f to the 4 because it really tells you what this guy is, and you can see that the field. So here is where the powerful representation comes into play. You see f16 here, they laid out for you. This is why this book is so beautiful. This is the 16 different 4 tuples.
Yeah.
And as a polynomial, they don't write it with the x, but they write it as in terms of alpha, where alpha is the root of this polynomial here, alpha to the 4 plus alpha plus 1.
Okay.
Right? Which
Yeah.
is the same thing.
Right.
Now, if you imagine that alpha is a primitive element, we also said primitive root means you can generate the whole thing. So, then 0 is 0, 1 is 1. This is alpha squared, alpha to the 3. But then, of course, the alpha to the 4 is equal to alpha plus 1.
Mm-hmm.
So then that's alpha plus 1, it's alpha 4. Then you have alpha plus alpha squared, that's alpha fifth. And so on. You have the whole representation as powers of alpha as well, which is going to be easier to work with.
Yeah.
Okay? So we kind of step away. So here you can see exactly that that's the coefficient, right? 1 is 1, alpha squared, alpha cubed. And then you see this is 1 plus alpha because it's 1 and 1, right?
Right.
And this is like alpha squared plus alpha cubed because it's like these are the coefficients. So you go from coefficients, binary, to polynomials and vice versa very easily. And for this you have to like figure it out by doing all the divisions and then see which element is which power of which.
Mm-hmm.
So once you have a representation as powers, then it's very easy to operate the field multiplicatively.
Right.
And you can use this representation is even easier to work additively. I think we already went through this in one of the previous lectures. Okay, so once you have this laid out, then you see that each 4 tuple corresponds to a specific field element as a power, and that's what we want to do.
Okay.
Okay?
Yeah.
Because now we can come back to that like I plus j, f of I plus f of j, and then see exactly what this f is going to be, so that I can actually solve that system. Okay, so let's go back out. Yes, because I'm looking for a way to solve this. Okay, and so once I have this field representation understood, okay, how can I solve this? What is a choice for a function f of I? Should this be like a multiple of I, for example? Well, if I choose a multiple of I, then my system here becomes I plus j, and then ci plus cj. And obviously that's the same as c times I plus j, so then I cannot solve this. Because this is a redundant system. It's just a multiple of the first equation. I need 2 different equations. So I cannot choose just a constant multiple of I. I can also not choose like I squared, because what happens is then I get I plus j squared. Because this is I squared plus j squared in this field. Because the plus 2ij is 0, because we're working mod 2.
Right.
Right? Remember that this is f to the 4, so the characteristic is 2. Yes, these are binary strings, so it's f16, but it still works modulo 2, right? The characteristic is this like intrinsic property. The nature of the field is binary. So
Yeah.
all the squares are like equal to the sum of squares, which is kind of weird, right? But it is what it is. So again, we get a redundant equation, so I can't use that. But maybe if I choose f of I equal to I cubed, then I get actually I plus j equal to z1, and then I cubed plus j cubed equal to z2, and this is a properly defined system, and I can solve it. And I can solve it in this way. Well, then I can write that z2, for example, is equal to I cubed plus j cubed, which we know is I plus j, and then I squared plus ij plus j squared. This is a calculus or College algebra thing, right? Well, what is ij? Is I plus j is exactly z1, this, and this is actually z1 squared. It would be I plus j squared would be this, would be two of these, right? So there's one of them missing.
Yeah.
And I put here plus because plus and minus is the same. Again, we work modulo 2. So it should be z1 squared minus ij, but it's plus ij because, again, I'm characteristic 2. Okay? And so this means that effectively, now that I can look at this and that, what is ij is z2 over z1 minus, which becomes a plus, z1 squared. Okay. And now I have a formula to express the product of the two, and a formula to express the sum of the two.
Yeah.
What can I do with this? It's a polynomial, right? You know that the polynomial is like 8b, you know that the polynomial x plus a and x plus b becomes x squared plus a plus bx plus ab, right?
Mm-hmm.
So same thing here, that's what I get. It means that I'm effectively looking for the roots of x squared plus I plus j x plus ij, which is x squared plus z1x plus that. And this is interesting now because how can I then find the I and j? Right, once I get my, remember that this is what I get out of the syndrome.
Right.
So the syndrome gets me this, which means I can set up a polynomial and then look for roots.
Yeah.
So this is, now this is like properly clever, because before it was like, okay, what can I decode? Oh, I can write down the whole array and just look for the word.
Yeah.
Well, okay. Second thing, I can look for the syndrome and then like, still like I have to write out the thing. Oh, Hamming codes. I can actually like look for the code word and then take the syndrome and look in the columns. That's still kind of like very intuitive. Now we're like leaving the realm of intuitive. Like this is actually clever now.
Yeah.
I can take my received word, compute the syndrome, that will set me up a polynomial, and I can look for roots. And then, of course, what happens is, if there are no errors, z1 and z2 are actually 0.
Right.
Like my syndrome is going to be 0, 0 as field elements. So this should be like 0, 0, 0, 0, and then 0, 0, 0, 0, right? I can always think in this like dual way. These are like elements of F16,
Mm-hmm.
the top one. These are actually the binary strings.
Right.
But otherwise, I could have either 2 roots or 1 roots,
Mm-hmm.
because it's a quadratic polynomial.
Yeah.
And so what happens is that if I have a single error, then z2 is actually I cubed. It's the same as z1.
Okay.
And that means I have a single error. Otherwise, I have 2 distinct errors. So essentially, how can I decode these kind of codes, which are called BCH for Bose, Ray, Chowdhury, and Cunningham, I hope I spelled it correctly, is BCH codes.
Okay.
This is a type of 2 error correcting
Mm-hmm.
BCH code. We will see in a minute how we can generalize them. It gets easier and easier because as we generalize, the mathematics gets more complicated, but the idea gets more intuitive. So how do we compute? Basically, step 1, compute syndrome S, which is H times Y transposed, which essentially we said is going to be Z1, Z2. Z1 is the first 4 positions, Z2 is the second 4 position. So basically we have a 2m by n code, right? We compute the syndrome. That's going to be, say, a string of length 8. The first 4 elements are my first field element. The second 4 are my. So I have to be nifty with this, going back and forth from binary strings to field elements, right?
Yeah.
So I take the first 4, it becomes a field element. The second 4, it becomes another field element. And now I work just in the field, right? And either I get z1 equals z2 equals 0. Okay, there's no errors. Or z1 is not 0, but z2 is actually its cube. Well, then I know that the error is of the form I cubed. There's only one error, right?
Yep.
So there's only one error at position I. Or z1 is not 0, z2 is not the cube of z1. Then I have two distinct errors. Form quadratic and find roots. And I expect to find exactly two distinct roots at positions I and j. These are going to be my errors. Okay? Of course, this is a quadratic, so there's also the case that this has no roots. This quadratic has no roots.
Yeah.
Or also it could happen that z1 is equal to 0, but z2 is not. And then what happens is that there is at least 3 errors there. Okay, so I can tell you something went wrong. You put too many errors. I cannot correct this. Cool.
Yeah.
And so yeah, so basically you can treat this as a binary code, but then you really interpret it as a query code over 2 to the m. Yes. So in fact, you can think of your code in this way. Remember, we have that parity check matrix. We can write it in this way: 1 alpha squared, alpha cubed, all the way up to alpha to the 14, which is the last element, right?
Yep.
This is not the same that we had before, because before we had it in kind of like numerical order, right? So 0001, 0010, and so on. These are not necessarily these ones. They are not in the same order, right? As binary strings. So we just kind of rearrange them. And then the second row we said is the cube. So it's 1 cubed. And then it's alpha cubed. And there's alpha squared cubed, which is alpha 6. And then alpha 9. Okay. All the way up to what is alpha to the 14 cubed, that is alpha to the 12. Okay, remember you have to reduce modulo always.
Yeah.
Okay. So that's going to be my parity check matrix there. Okay. And of course, what's going to happen is that this not all powers appear here, because for example, the next one is going to be alpha to the 4, which gives me alpha 12, and then alpha to the 5 gives me alpha to the 15, which is alpha to the 5 cubed. Right? But actually, this is equal to 1, because alpha to the 15 is exactly the next power, right?
Yeah.
Remember that this is f16, so p minus 1 gives you the 1. So then here you get 1.
Yep.
And then they repeat. So there's like 3 chunks: 1 alpha, alpha 6, alpha 9, alpha 12, 1 alpha. But that's because alpha is not a primitive root, right, in this case. So, sorry, not alpha, of course. Alpha is a primitive root. It's alpha cubed that is not primitive.
Okay.
So if alpha cubed was primitive, then here you would have all distinct powers as well.
Yeah.
But for ease of description, we chose the function f. Remember with the function f to be I cubed.
Right.
Then here we're doing basically the series of powers of alpha cubed, and that's not primitive itself. If we chose, I don't know, alpha to the 5th or something that is primitive, then we would have had like different way of generating this BCH code.
Yeah.
Okay. And when you do expand this onto binary, then this gets you the matrix H as a binary code, so you get like 1 0 0 0, and then this is also 1 0 0 0, and then alpha is 0 1 0 0, and then here you get alpha cubed, which is 0 0 0 1, and so on. Okay.
Yeah.
These are the topmost element, and these are the last. So then alpha to the 14 is 1 0 0 1, and then alpha to the 12 is 1 1 1. Okay. And you get like your big binary matrix.
Yep.
Okay, and this is how the BCH code work. For an example, suppose that you receive a column and two errors occurred in positions like I equals 6 and j equal 8, right? Then what you get is exactly z1 equal 1001, which is alpha to the 14, and z2 is 0100, which is alpha. So your received word, you receive it, you compute the syndrome, you get this. Right?
Mm-hmm.
You split it in two, and then you transform it into field elements. Right? This is z1 and z2, and then you can just write z2 over z1, which plus z1 squared, which is that term at the end of the polynomial,
Right.
right? Which is also alpha to the 14 after you do your calculations. And so the equation that you set up is x squared plus alpha to the 14x, which is I plus j, and then plus alpha to the 14, which is I times j. In this case, it's kind of a strange example, they're equal to each other, but it's okay. These factors as x plus alpha 6, x plus alpha 8. So once you find your roots,
Okay.
alpha 6, alpha 8,
Mm-hmm.
position 6, position 8 is the mistake. Okay.
Yeah.
And again, I'm using here binary, right? Of course, that's x minus the root, always when you factor the polynomial, but like minus plus in binary is it's always the same.
Right.
Okay. So cool. So basically, in our construction, the length had to be 15, so we could do the finite field construction properly. In general, what we can do is we can do this for any m, right? And then the length is going to be 2 to the m minus 1, right? And then the parity check is going to be of the form 1 alpha, alpha squared, all the way up to alpha 2 to the m minus 2. And then here we get the cube, 1 alpha cubed, alpha 6, all the way up to alpha 3 times 2 to the m minus 2. Okay, so we can get this for any m, and these are always double error correcting BCH codes. Okay, so I want to show you a couple more things. Basically, okay, let's go here. Now we can correct two errors. It's a step up, it requires us to be clever, but I can in fact improve this. So how can I generalize this class of codes? First of all, we hinted before at cyclic codes, right?
Mm-hmm.
We said that these codes are cyclic, the Hamming ones. Turns out the BCH are also. In general, a cyclic code can be defined. Well, we can actually expand this later. I know that we have all the time not to do that. Okay, so how can we expand the BCH codes? All these codes are going to be cyclic, which means I can also choose them in a way so that the matrix is circular. Okay, so now suppose that I have cyclic codes. I have to say these things. So basically, whenever we have a code word C0, Cn minus 1, we also have the shift, and it's also a code word. So that means that Cn minus 1, C0, all the way to Cn minus 2 is also a code word.
Yep.
Okay. Okay. So basically, what this reminds us of is that if we associate this to a polynomial,
Mm-hmm.
C0 plus C1x plus Cn minus 1x to the n minus 1,
Mm-hmm.
right? What happens is if we multiply by x and call this like C of x, then this word becomes x times C of x. Because here I get C n minus 1 x to the n, And if I'm working modulo x to the n minus 1, then x to the n is equal to 1, right?
Yes.
And then this kind of thing wraps around. So I multiply the whole thing by x, I get this becomes c to the n minus sigma, then this becomes c0x, this becomes c1x squared, and so on. And so the polynomial rotates. So when you take polynomials and you multiply by x, what you're doing is you're rotating by one position. If you're working, now we are in a field, right? Field of polynomials, but you have to work modulo x to the n minus 1.
Right.
So if you do that, then this word maps to that word once you multiply by x, and so on. And then you keep shifting, multiplying by x squared and whatnot. Multiplying by this by x squared is like multiplying this by x, right? So that makes sense why you get the circular form, because you have the first row, then the second row is multiplied by x, then you multiply the second by x, which is the first by x squared, and so on, and then you get all the shifts, right?
Yeah.
And so your generator matrix is going to look like C0, Cn minus 1, and then Cn minus 1, C0, Cn minus 2, and then Cn minus 2, Cn minus 1, C0, Cn minus 3, right? And you get your matrix in this way.
Yes.
And so what this means, in fact, what you can do is that this code, remember that the code forms a subspace of the space. Now we're working in this space, so the code C is part of this, and it's in fact an ideal, which is like kind of like a subring plus extra properties, right? Part of this code. And so basically you can identify really these codes as these particular types of sub-rings of this polynomial ring. Okay. And you see, you already have here an idea of what the generator matrix should look like. And in fact, we do this G, and we choose a particular polynomial G of x, which we call the generator polynomial, and that is what defines the code.
Yeah.
And then you can show that every code word is basically like x to a certain power times G of x.
Yeah.
These are going to be the rows. But then what is the code? It's a combination of the rows. So it could be like x g of x plus x squared g of x, right? And so you see that g of x actually defines the entire code, because then this is x plus x squared g of x. And this is some other stuff, right? So then the generator polynomial defines not only the generator matrix, but actually every word is a multiple of it.
Okay.
Okay, so in the generator matrix you have the simple multiples, and then all the other code words are combinations of these. So these are very cool, and we can use this idea to generalize the BCH codes. And I don't know that I want to say more than this about cyclic codes, but essentially what we can do is this. Suppose now that I take a cyclic code, I want to have a better BCH code that corrects more errors. And suppose that I'm able to find a G such that I know that G, so is going to be my generator polynomial. I want to define a code with this G. And I want that G, say like alpha to the B is a root. So one of the field elements, right? Remember that before we had like these field elements being roots, right? And then now I compute G also in alpha to the B plus 1, all the way up to like alpha to the B plus delta minus 2. Okay? And suppose that by pure chance I find that all these successive field elements are roots. Okay? Then, where these B and delta are some parameters, then essentially I have t minus 1 consecutive powers that are roots. And then what I can claim is that the minimum distance is exactly delta. Or actually is at least delta. And the proof of the theorem is a little bit more complex, but essentially if you have a code word C, C0, Cn minus 1, then that means that C, seen as a polynomial, when we evaluate it in like alpha to the b, gets me 0, right?
Okay.
Because remember, words now are polynomials, so evaluating means multiplying, and the same happens for c in alpha to the b plus 1, and so on all the way up to here. Okay, but again, if you imagine that this is your polynomial here, what does it mean to evaluate in alpha? It means that you replace x with alpha, right? So you're doing c0 times 1 plus c1 times alpha plus c2 times alpha squared and whatnot.
Right.
So that means that if I take 1 alpha squared all the way up to alpha n minus 1 b, and I multiply this by c0 cn minus 1, right?
Yep.
This is c0 times 1 plus c1 times alpha. This is exactly c evaluated in alpha to the b. Okay? And then I do this for the next one, and I get 1 alpha to the b plus 1, right? And then alpha n minus 1 times b plus 1. And then I do it until the last part, which is 1 alpha to the b
You're
plus
starting to go off the screen just a little bit.
yeah, minus 2. And then alpha to the n minus 1 times b plus delta minus 2. And this corresponds to evaluating c in all these consecutive roots, which are the roots of my generator polynomial.
Uh-huh.
And this is 0, so I can take this to be my h. Okay? And if you look at the form of this matrix, when we stop at the first 2 rows, that's exactly what we had for the 2 error correcting code, BCH before. We had 1 alpha squared, right, all the way. And then here we have the next one. So this is kind of the generic form of a BCH code that can correct, say, up to t errors.
Okay. Yeah.
Okay, and hopefully this makes sense. And this is called a code of designated distance delta, because delta is exactly what you're shooting for. Okay, and then t is going to be obviously like delta minus 1 over 2.
Okay. Yeah.
Okay, so what you're gonna have is you're gonna have a parity check matrix that has b plus delta minus 2. Sorry, it has d minus 1 rows here, or delta minus 1 rows, and then the length is going to be n minus length n minus 1 times. Okay, so this BCH code has dimension as length n in dimension a, which is at least n minus m delta minus 1. And again, this comes back to us if we put that the previous one were meant to have, for example, designated distance 5, so that I can correct 2 errors, and then m was 4, for example. And then I get n minus 4 times 4, 16, and then I get my dimension there. Okay. So this is how I generalize the concept of the BCH codes. And of course, now to decode such a thing, the algorithm would look like similar to what I had before. Before I had to solve a quadratic,
Right.
right? But now it's kind of the same idea. So I'm just going to write a couple more things. So basically, what happens is that now what you do is the first step is always compute the syndrome S, right? And then what you can do is you can basically set up a polynomial, and then you like set up a polynomial, which again before was a quadratic, and now is going to look like it's going to be a polynomial like sigma of, well, x is not the, I mean here they call it sigma of z, whatever, right? Which is going to be of degree w, where w is the number of errors you're trying to correct, right? So before we got a polynomial of degree 2, and now it's going to be a polynomial of degree w, and actually there should be really like the product of like z plus first root times z plus second root. For example, in the first case it was like this, right?
Yeah.
Now we can expect that this is like z plus alpha w. But actually, rather than writing it in this way, we write it like a z plus 1 over alpha 1. It's just easier for the representation of the code.
Okay.
It may look like less intuitive, but it is kind of like we write it in this way. And then the roots are not exactly the alpha 1s, but they're like the reciprocals. But it doesn't matter. Once we find the roots, then we just take the reciprocals.
Yeah.
And so we can write this compactly as the product from 1 to w to say like 1 minus xi z, but the xi is exactly 1 over the alpha I that I'm looking for.
Yeah.
And this will be a certain polynomial sigma I z to the I from 0 to w. Okay, polynomial degree w. So what I get is this polynomial, which is just I compute the syndrome, right? That gives me a polynomial which is of this form. And I know it's the product of w separate factors, each of them corresponding to the reciprocal of one root. So then I have find roots. And once I find the roots of this polynomial, then I can get the reciprocal of the roots are exactly where the positions of the error.
Yes. Yep.
So
Yeah.
it's kind of like a generalization of the process that we had before.
Right.
Remember that basically you compute a syndrome that gives you a polynomial. How you compute this polynomial, already the quadratic one was not obvious, right? Because the polynomial was like x squared plus z1x plus z2 over z1 plus z1 squared.
Yeah.
Right? So it's not obvious how you can get this from the syndrome. The syndrome in this case was z1, z2.
Right.
Right? But there is a process for transforming your syndrome into this polynomial, which is called error locator. And once you have the error locator, then you basically just find the roots. Finding the roots can become, of course, complicated, right? If first of all, you're over a finite field, and you don't really have the quadratic formula or anything like that anymore, right? So,
Yeah.
so the algorithm gets more and more expensive, more complicated, but it is still kind of efficient, and then like you can recover the errors. So algebraically, you have a way of recovering the errors.
Right.
And then much of the development of these codes become improving over the BCH to find other class of codes which generalize this idea, make the algorithm more efficient, exploit some algebraic properties of how you construct the matrix and whatnot. So you go from BCH to what is called Reed-Solomon codes, RS, which are a generalization. You can then generalize this to GRS, which is generalized with Solomon, and then you have like many constructions of codes that get like different types of flavors. You add one property here, add one property there, and you see where this is going. So then you actually get codes that correct like a proper, decent number of errors, and they do it using strong algebraic properties. Okay, so we went from like, simply recognize the column to, it's a sum of two columns. Let's try to solve this simple system. We do it with a quadratic to take this process to the power. So
Yeah.
next time we can, sorry I went a little bit longer. Next time, now we have at least an idea of what the decoding process looks like. And next time we say, okay, now we have codes that are defined in this way. We know that for some of them we have a decoding algorithm which can be more or less complicated, which can correct up to a certain predetermined number of errors, depending on the mechanism. How can we use this in cryptography?
Right.
To create a trapdoor and to beat encrypt on it.
Mm-hmm. Okay. Yeah.
So that should make sense. There's of course, as you can imagine, a lot of theory on how to construct such codes and design them and decode them and improve them and stuff. So this is just to give a flavor of what it happens. Okay. See you next week.
Thanks.
Appreciate it, Professor.